So, thanks a lot. I think, can you hear me down there? I prefer without. Can you hear me? Yes. Okay. So, thanks a lot for having me here. I'm really honored by that invitation, and the first time I have contact to this society, and I appreciate very much what you have achieved here, what you are running here. The talk I will give will be about early electrodynamics, and the aim of my talk will be to situate Felici's contribution a little bit more specifically within a wider picture of the development of that branch of physics. I shall really focus on theory and experiment and not about Felici's position in general, which we have heard so much about. Again, this is in some way not trivial, since now we are focusing on academic research with theory and experiment, but this was a time when, of course, electrical technology had dramatic expansion. So it would be interesting in all those things to include much more than I can do today, electrical technology and the ways engineers thought about it. But I won't do that. What I will do, if I manage to be in time, first to give you a broader view on electromagnetism and electrodynamics at the time, from the beginning to Felici's time, in 3 steps, as you will see, and try to situate Felici's position in all that. I start right away with early electromagnetism, which you know already, but nevertheless it's not unimportant even for understanding Felici. When the news of Ørsted's discovery spread in 1820, this came very much as a surprise for most of Europe. It had been electromagnetism, such interaction had been sought for 20 years, since 1800, since Volta's invention of the pipe, but in Wayne and in particular in Paris, people had claimed such an action is impossible. Of course, you might imagine then Ørsted came with his news. You see here various presentations, a later one, and a real presentation of the battery and of the general constellation. Our Ørsted had been right that his finding has often been told. I won't do that, but just let me say, Ørsted himself knew very well what he has achieved. He did everything to publish as quickly as possible all over Europe, and well aware of what sensation it would cause. And he was right in his idea that would cause much sensation and much resonance and even a challenge. So the major challenge is that he had found something that had been sought in vain before him. Humphrey Davy, one of the British researchers who went on it, said, this discovery opens a new field of inquiry, into which many researchers will undoubtedly enter, and this was actually the case. So what was the reason why it was so, even so challenging? As we saw, and as you know, electromagnetism has a complex spatial arrangement. You have the wire, you have current direction, which was ill-defined at the point. You have the direction of the needle, and you have the direction of the movement of the needle. So, and at that time, even in the mathematics of the time, you didn't have concepts that would allow to express those things quite densely. So the descriptions of this time you see are very long. They take reference to the compass direction, etc., etc. So there was a painful lack of concepts to deal with that spatial complexity. Even more so, the effect had one feature which was really puzzling for most. This was this is the current, the magnetic needle above the current. If it switches in that direction, if you do it in the same distance, just below the current, it moved in the other direction. Arago, I show you the highlighted that point very strictly. When the wire is below the needle depends in the direction opposite to that assumed when the wire is above. Why was that so striking? It was visibly incompatible with the general idea that all interaction, all physical action depended only on central forces, that itself depended only on the distance. So direction and position came in here as a relevant factor, and there were no means to grasp that. This was particularly true for Paris, where of course you had fully mathematized theories based on these central forces. So this makes clear how big the challenge was. And to describe the reaction very roughly, you could separate between the reaction in Paris, on the one hand, because they had Paris was a special place anyway. It was the place of mathematical physics, and the reaction in the rest of Europe. This is only slightly overdrawn. I shall go through the two of them with a final focus on the first topics. Reaction in Paris. Paris mathematical physics in the Laplacian spirit was prevailing. This means reduce everything to central forces that depended only on the distance, because then we have mathematical instrumentation dependently available. And then mathematical physicist in Paris, out of the Laplacian school, was Biot, Jean-Baptiste Biot, and this is what he wrote: what to do in face of the new effect. The first thing to be done was to discover the law according to which the force emanating of the connecting wire diminished with the distance between wire and magnet. This was the thing the Laplacian school wanted to have. Okay, Biot did what he followed that program. I won't explain in detail, I cannot explain in detail the apparatus. This was his first apparatus. He collaborated with his assistant, then assistant Felici, and they used an old measurement principle varying the distance between wire and magnet. Here is a small magnet oscillating, and they counted the time of oscillation independent of the distance between wire and magnet. First, with a straight wire, this is the current carrying wire, and then with a wire that they get an angle because they realized, okay, the angle between the plane of oscillation and the wire may play a role. They describe how difficult it was to carry out those measurements, mainly for technical reasons. Batteries at that time were not constant for even a moment. They decreased in intensity from the very first connection. And how to do such measurements in such a situation? So they invented very complicated procedures. In the end, they claimed that these to be successful. They discovered 1 over R law between the wire and the magnet, and reduced it mathematically to a 1 over R square law for the infinitesimal element, magnet and of the wire. And with the second series of experiments, they included an angle, and this is the well-known result they found in the end, 1 over R square, and the sign of the angle coming in. Nowadays, we write that law with the vectorial product. Of course, it was far away. After that, Biot left the field. This is what the Laplacian program had required, and he had fulfilled it. And within a few months, in December of the same year, he presented that law. Let me, before I move on, let me point out one feature of that. This was a great success indeed. but it had its cost. You never cared about the full spatial complexity that the electromagnetic effect offered when in various positions of needle and wire. This is a highly symmetrical position. He had analyzed, so the cost was focusing on one highly symmetrical position for elaborating the law versus exploring the full spatial complexity as more or less everyone else did in Europe. Okay, this was Bio. Bio was not the first one, it was not the only one in Paris. The other one, the other initiative to jump on this new phenomenon was by Ampère. Ampère was not well known in Paris at the time, or at least not in physics. He was a mathematician at the Congresso. He hadn't done experimental work, any experimental work before. He hadn't done work on electricity and magnetism, so it came as a surprise that he went in. There are many ideas why he did so. I will go into that. Ampère is, of course, the one who is well known for his electrodynamics. So I will focus a little bit on Ampère, and because he's very important for Felici. Ampère started with exploring the new effect. He, together with the instrument maker, always the instrument maker alone, he would never have succeeded. He designed the instrument to separate the magnetic effect of the Earth from the one of the wire, this astatic needle. He explored by varying many parameters the spatial constellations. His idea was to formulate a law or a set of laws that would regulate that interaction. He called those the fait général, and was looking for these general facts. One of them he even spelled out, action directrice, he called it, and it's, some of you might still know that rule, the swimmer, so-called Ampérian swimmer rule, where he defined the direction the needle would take in face of a current, and he could do so only by introducing new concepts. He spoke of the left and right-hand side of a current, which nobody had done before, and he used a strong imagery for that. Again, I won't go into it. This is Ampère's first phase of research, only a few weeks. This was even before Bio's arrival in Paris. Ampère, that phase of research came to a sharp end when Ampère made a discovery by speculations he did in parallel. He discovered the attraction and repulsion of two currents without any magnetism involved. So that was a totally new phenomenon. This is Ampère called this Electrodynamics. It's a dynamic interaction of electricity. And he did it first with a spiral arrangement on the left-hand side, and then with a well-known straight arrangement, which with much weaker effects. From that point on, he was absolutely decided to leave his former agenda of exploring spatial constellations and throw himself fully on the idea to find a law for that electrodynamic interaction. The basic idea was again, now coming back to the Laplacian surrounding, who was living in, he had not been part of that before, but again, do it with central forces, depending only on distance. He quickly realized this doesn't work with currents. We have to introduce angles. For the distance dependence, he took the 1/r² law absolutely for granted. He never checked them. He took it for granted. And the great challenge was to find how that force depended on the complex constellation of two angles. So his point-like sources of the central force were not points, but infinitesimal elements of a current. How to find the angular dependence? The Ampere had a speculated formula in mind. You see the angles. This is my drawing. The angles given here, and he wanted to find, give it as an experimental support, how to make a measurement device. Compare the devised one. Of course, again with the instrument maker, again I cannot go into that. It's again a similar principle as Bio had taken with electromagnetism, now transferred to electrodynamics. We have that picture. We have no report whatsoever of Ampere on it. I interpret that as a very clear sign this machinery never worked. It never produced stable results. It was not successful. And the technical reasons are obvious. It's not only those problems Bio had described, but the most striking impediment, of course, is you have to have movable electrical wires with a maximum of electrical conductivity and a minimum of mechanical friction. Do that. So it was really Ampere later on tried to find solutions for that. They had solutions already here, but they didn't. So Ampere was in the cul de sac. He didn't measurement didn't work. His idea then was try to mathematize, try to find the mathematical formula for the angles without measurement. How to do that? He postulated what later on was called the principle of addition. I have written down here. The force exerted by a current element is identical to the superpositions of the forces exerted by its components or its projections. This is not the mechanical parallelogram of forces. This is a statement about electrodynamic force, the force under investigation. Ampere was clear about its speculative character. Nevertheless, having that speculation, that statement would allow him to work no longer with a full complexity. He could reduce the complexity to he could work with the projections. This is his drawing. You have here the current element. Here is the current element, and you can just project it onto three axes, orthogonal axes. And for those, he was clear to have was convinced to have an electrodynamic idea. So full attraction when they were parallel, the two elements, full repulsion when they were anti-parallel, and zero action when they were orthogonal. And these 3 points, which were all qualitative, did suffice then to formulate the law. All the rest was mathematics, and it's a challenge, but not too complicated challenge. Here, this was the first law he had published, and then he had published actually a few days before Bio. There was a race between the two for electrodynamic action. Full success. Again, Ampere was aware. Okay. There should be some experimental support for that. And this means some experimental support for the addition principle. How to do that? Since direct measurement was impossible, Ampere had the idea of equilibrium or zero experiments. Arrange currents and wires in such a way that the resulting summary force of the movable wire should add up to zero, if the theory is correct. And this is what he did. He invented one equilibrium experiment after the other. The most famous one is the one to support the addition law itself. Again, so the basic idea is here we have a movable loop here you have a complicated winding of electrical wire. On the other hand, in the same distance, on the other side, you have a straight wire, and you, if you do it correctly, they should exactly compensate each other's action, and so this loop should not move. This is what we found. This is so the basic idea is to have 0 experiments in order to avoid measurement.
Sorry, what are GH and M and so on?
Sorry?
In the formula. GH and M.
So this G.
No, entering in the formula for the first loop.
Ah, for the first law.
Yeah. H is a.
Oh, yeah, this should be in the 2 currents. The strength of the intensities of the currents.
Okay.
This was his. Later on, he would rewrite it in
No,
I1 and I2. So, I think then Ampere was done in a way. Was through with this law. Later on, he would, under the impression of this Paris environment, he would reformulate the law as you see in differential form, bringing in more sophisticated mathematics with differentials, and in the end replacing the trigonometric function by directional derivatives. His final publication in 26, 4 years later, 6 years later, had a very special title. Théorie des phénomènes électrodynamiques uniquement déduite de l'expérience. This is a very strong claim, and he started with a strong claim, with a methodological claim. Everything he said, everything I'm presenting here is directly derived from experiments. This is a striking statement, given that he presents exactly 4 experiments in the book, one of which he confesses he hadn't time to perform. Okay. This is so as an inductive statement, people quickly realize, many people, there might be a problem. It's not that sensitive problem. All of those experiments were in 0 experiments. There was again no measurement involved. And the central experiment was exactly the one I had shown you, the proof. The proof of the addition principle, called now the proof. So this is what you see as development of electrodynamics in Paris. Let's see and have a very distant and overall look what had been electromagnetism at other places in Europe. And this had been a broad exploration about materials, about batteries, about wires, about dimensions, spatial constellations, etc. There had been one specific strand in galvanometers. I show you here 5 names of people who had, in the beginning, independently of each other. The galvanometer had been invented in 1821 by 4 researchers independently of each other, which is striking. Nobody here in Italy had developed a much more sophisticated galvanometer in 25. And there had been electromagnets involved. Of course, you could use that electromagnetic action to create magnets. Barlow in London and Joseph Henry in the US had been very famous for that. But you see, there is no mathematics involved. Outside Paris, there was more or less no. One point to be mentioned about the spatial constellations was a quite unknown guy at the Paris the London laboratory, Michael Faraday, chemical assistant over there. He had written in 21, had been asked to give an overview review article on electromagnetism, and he focused, as the table might illustrate on the left upper side, he focused very much on spatial constellations. This is what he tried to make sense of. With his own research, shortly after that, he was driven by the idea to make sense of the spatial constellation and ended up with a strong claim and say the basic action of electromagnetism is not attraction and repulsion, but a circular motion. And it is, he invented the first electromagnetic rotation device. Okay, let's keep like that. Now my next chapter would be the induction. This very same Faraday, as we know, discovered electromagnetic induction in 1831. Again, an effect that had been sought for since Ørsted and sought for anyway. The way Faraday had been taken, we don't know, but he discovered an effect, and the effect had more challenges than solutions. It was a very complex geometrical constellation. Magnetic and electric effects were not separated, and what puzzled him most, the effect was transient. Only when you switched on or switched off the inducing current, you got an induced current, but not when the inducing current was just running. He was very puzzled about that, even so far that putting in question the very principle of causality. What's going on? So he decided to do intense research before publication. When he published in 6 months later or so, he had an awful lot of experiments. With Faraday, he had the advantage to have his notebooks. And we see how many experiments he had done so far. His basic idea, the goal had been to formulate an induction law, a law of induction. And of course, Faraday, a self-taught chemist, had no mathematics whatsoever. He never thought about giving the mathematical law of induction. When he gave the law of induction, this is his famous figure. He formulated it in terms of the so-called magnetic curves around the magnet. And the basic idea is this is the inducing wire in the form of a knife, which is perpendicular to the plane here. You see here the sharp side and the back side of the knife. And only when the knife is in such a way that it cuts, virtually cuts the magnetic curves, then you have an induction effect in more or less what we call the three-finger rule. This is a qualitative statement, plus it takes use of the magnetic curves. Magnetic curves were not unknown at that point. I just show you a picture of Einstein's Encyclopedia Britannica some years before. These curves were well known, but they were, of course, taken as an epiphenomenon. This is nothing of any physical importance. And what Faraday did, exactly turning that meaning around, giving them the central importance as being a frame of reference in which the induction effect would be formed. Very strange from most of his contemporaries. But at least he gave what he himself called a law of electromagnetic induction. And it worked quite generally. He could even give it for voltaic induction, induction of currents by current, by using the lines of force around the wire and make them expand and collapse when the current was switched on or off. So he gave a quite general law, but qualitative. So what were the reverberations of the publication? First, a technological. Only a few months later, the effect would be had been used for creating the very first electromagnetic generator by a Paris instrument builder, Pisa. Fascinating effect, and of course, the thing that would change the world quite quickly and give electrical technology a boost. But what was the reaction in academic physics, so to say? Most people, again, many people worked on it throughout Europe. Again, quite the same as we had before. They were exploring about materials, about batteries, about wires, about dimensions, spatial constellations, etc., etc. there were various attempts at defining the direction of the induced current, because this was, of course, the great problem, the great challenge. One of them by Mogli and Antinori, in Italy again, and by Lenz, that was already mentioned. Just to give you an idea how Lenz formulated his results, you see, I don't know, perhaps I will. If a metallic conductor moves near a galvanic current or a magnet, the galvanic current gets induced. It is directed in such a way that it would have produced in the wire at rest such a motion that would have been exactly opposite to the motion of the conductor, assuming that the wire at rest would be mobile only in the given direction and opposite. You see, it's quite a complicated formulation, and it's a formulation, again, there are more experiments in Lenz than would be later recognized, even by Felici. Felici said no experiments, which is quite untrue. Lenz had many experiments to come up with this rule, but nevertheless, these were the attempts to formulate induction. This held for quite a while. One, to continue working on electricity and magnetism quite constantly and quite densely was, of course, Faraday. I just give you the idea. Faraday used the idea of light or magnetic curves, or later renamed lines of force, in many fields. Electromagnetic induction, as we have seen, lines of electroinduction, namely electrostatics. His magneto-optic effect that he had discovered in 1845, he formulated with the terms of lines of force, and also the law of Dyer and parametric behavior in the same. He constantly published his results in the field of topical transactions, and at least in Germany, they were constantly translated and directly translated into German. I don't know about the French and Italian scenery. There was a peculiar resonance to Faraday. He was cheered and highlighted, praised as an experimenter with all these new discoveries. At the same time, it was complete silence about these strange concepts he had, about these magnetic curves, lines of force. There is a quote by William Thomson, then rather young. He found himself much disgusted by Faraday's way of speaking of the phenomena, for the theory can be called nothing else. This is by someone who knew the mathematical physics of the time. So complete dismissal. This is something we shouldn't even speak about. I will come back to it. The scenery was changing by the mid-1840s. Again, now we can, you see, I make now a divide between Britain and the continent. In Britain, we see, again, Faraday is the most important figure, is one important figure. Faraday gave in the early 1850s summary account of his view on electricity and magnetism, and described very much, in much detail, what are the features of these lines of force. They have definite direction, they have a density in a certain realm of space. This he called the field. He spoke of electric and magnetic field. There was a conservation principle he formulated. There were conductivities in bodies for these lines of force. That is here, they pulled them in or pushed them out. There was the idea how bodies move under the effect of lines of force. Faraday went so far as to say the concept of magnetic polarity loses its importance. It's true that magnets have their pole, but only some of them. Diamagnets don't have poles, and nevertheless fission. And there, in the end, this famous relation between electric and magnetic lines of force. At that point, William Thomson, who had discussed, changed his mind. So, okay, there must probably something more in it. He was probably triggered by the conservation principle because he had found a similar principle before. And he triggered his young friend Maxwell, who was looking for a new field of physical activity, look at electrodynamics, and do it by Faraday. And Maxwell decided to do that. He deliberately decided not to read the continental approaches, which I will talk in a moment about, but starting with Faraday, and then we know the effect. Maxwell decided, okay, this conceptual framework is rich in such a way, I take the task to give them a mathematical form, which they are totally missing. Maxwell had the idea these concepts are very precise, but they are not mathematical. And Maxwell set out, as his nature says, to give them a mathematical form. And as you know, in four steps, starting in 55, 62, he gave his major publications. In the treatise, he gave the full set of what we call now Maxwell's form. So the field theory got a mathematical form, but Maxwell himself emphasizes again and again, all the experimental basis was done, and the conceptual basis in some way done by them. This was the British development. On the continent, people already started by the mid-40s to think about how to get a mathematical law of induction. We had already heard of Weber. He criticized, of course, he was admiring Ampere. At the same time, he criticized Ampere for two things. First, for his equilibrium experiments. He said, this is just missing the central point. Because if you do such an experiment, you should have an estimate how sensitive your apparatus is. There's nothing like that in Ampere. So Weber set on to say, okay, let's do real electrodynamic measurements, and he invented, jumping on a former tradition, what he called the bifilar magnetometer, or electrodynamometer, as he called it, a very sensitive instrument for with a mirror and a projection, etc., to measure, really to measure now electrodynamic effects. The other thing he criticized, or he stated in Ampere, of course, there was no induction in Ampere. And he set out to find induction law. And again, Weber gave, in the end, a complicated formula for electric interaction with Coulomb, Ampere, and induction all in one formula, much based on a physical speculation about the interaction of two charges. Weber was not the only one, as we heard. Franz Ernst Neumann, about the same time, focusing quite on a different. So Neumann was going back to Lenz and saying, okay, let's try to figure out how we could formulate that in a general manner. What we would say, this is a sort of potential calculus with potential functions. As you will see here, a double integration leads to that function, and then you can make the derivation of that function, and you get the electrical tension. Later on, 12 years later, Gustav Kirchhoff, a disciple of Neumann himself, who generalized that in 3 dimensions and introduced what we would call now electron potential. So even on the mathematical continental side, you find attempts to give the induction law a mathematical form. Very different from the British. Very. This is the place where we now we have arrived at Felici. We are the 3. Yes, this will be my final chapter. 3 final. These are the 3 studies that were mentioned already, and the only one I can read, I must say. I could read the French stuff. Felici published also in French, and many of his publications were translated into French. But that's the only one that was translated into German. And you see, my title is Amperian approach, and Felici was determined to do it like Ampere. Let me explicate in 4 points. First, his experiments. Again, he did no direct measurement. He gave even very clearly, more clearly than Ampere, he stated, we cannot do that. Batteries are much, they are not apt to them. They lose their power so quickly, we cannot do direct measurements. So what we do is we go for equilibrium, for zero experiments. In order to make them more convincing, he went to very strong batteries and very sensitive galvanometers. What he did not do, he did not mention Weber's criticism of all that. At least I didn't find. Okay, he did. The mathematical analysis, again, he was very close to Ampere. Of course, the entity to interact with infinitesimal current elements, this was common to everyone on the continent. And he made this addition principle that Ampere had introduced, again, explicit and took it for granted. The methodology, his methodological claims, again, are very Amperian. He claims to avoid any specific physical hypotheses about the nature of interaction between currents. And this is how we have, as we have heard, his criticism, at least in Weber. In Neumann, we don't find too many physical. Neumann was exactly avoiding those speculations as we had found in Weber. Weber was very strong in physical assumption and had been criticized even by Helmholtz. But Felici again wanted to stay out. Fourth point, if you look at the essential formulas he gave right at the beginning of his papers, but mentioned he comes back again and again to them in this particular, this little formula. This is the formula for the induced current, for the induced electromotive force, to be more precise, and this is for the closed circuit, this formula for the closed circuit. If you compare that with Ampere's latest formula, I'm sorry, I could have written it in the same way. You see, it's the very same style. So, what we could say here, we see the Amperian inclination in all these aspects. Of course, this is the late Ampere. This is Ampere of 1826 of this théorie électrodynamique uniquement déduite des expériences. This is what we see, a very strong reflection. Now I think we have a very clear idea, or we can get a clear idea of what Felici's place in that whole setting was. There was recently a publication of Felici, forerunner of Maxwell. I don't think that's a good. Of course, the talk of forerunners is problematic. Anyway, in history, it's much too teleological. Nobody presents himself as the forerunner of somebody else in the future. And of course, it would never have been Maxwell. There was no way Felici talked about magnetic curves, about lines of force, about field. This was completely alien at the same time as Maxwell. What they could say, however, he was the one, and the only one, to extend Ampere's approach into to make a full electrodynamic approach out of it, namely by including induction. I think that's a fair, might be a fair characterization of his contribution to electrodynamics. Let me ask, by way of an outlook, why did Felici choose Ampere? First, this is, of course, such historical questions of that type are always tricky. On the one hand, we can say he was unhappy with Weber for good reasons, others were unhappy too. He was unhappy with Lenz and Neumann. This might be not so good reasons, but still, we should have a look at how he came up, in, how the scenery here in Pisa had been at his chair. And of course, one pertaining thing was nobody had done measurements. He himself, not even, also, he did not do experiments, but he cherished the approach of zero experiments, and the only one who could do that, you know. Of course, one could even ask, why didn't he adopt Faraday or Maxwell? Maxwell wouldn't fit. It was a year later, but why not adopt Faraday's latest papers? I don't know whether he knew them. I just don't know. But even if so, the question would be very strange, because no physicist on the continent could do anything with Faraday's conceptual framework. It was just too alien, too incompatible with everything physicists, mathematical physicists had grown up. So this is a very nice example for what it means working with a paradigm, to use a Kuhnian term, or also with a thought style, to use a Fleck term. This, you cannot go out, you cannot step out easily. You can look at the other things and say, okay, I just have no idea what they speak about. This hints to a very specific point of history of electrodynamics in the second half of the 19th century. We have a coexistence, a parallel coexistence of two, let's take the Kuhn of two paradigms. I think Kuhn never thought about that they could exist in parallel. Both very successful, or less successful, as we see in the case of Felici, but they couldn't speak to each other. A situation that hasn't been analyzed thoroughly up to this day. We know how it dissolved in the end, starting from the 1880s with Helmholtz and Hertz, trying with, there are many things, but how that could work is an interesting question. And the most interesting question is, how could electrical technology develop in such a constellation where theories here and there couldn't speak to each other? And this is a question I invite everyone to have a deeper research on. I hope to find time to look at something. Sorry for
we thank Professor Steinle, but it's a very interesting lesson, and we have learned something about our teacher in that sense. Many of us have difficulty to close this wonderful story, and so we can start with some question. Only a few minutes, Anna, please. Thanks.
Concerning the zero experiment, Weber's objection was very sound, of course, because if you don't have a sensitive measurement, how can you tell that the result is really zero? You can tell that the theory is correct only up to the sensitivity of your instrument. But there is another criticism, another concern about zero experiments, and that is your setup. How well does the setup that you use really cancel the two effects? Because if the effect is not zero, because the cancellation is not good enough, you don't get zero and you say the theory is wrong. But the theory can be correct and your setup may be not good enough. There was somewhere some discussion about this issue or not?
Not in that time. The first to discuss that was Weber. Otherwise, Ampere was taken as a wonderful example of success.
Yeah.
And Felici took it like that, still, despite Weber's criticism. So all those questions of sensitivity, etc., in physics in general, they came later. Astronomy, of course, was always aware of that, but physics, in particular, I think this is exactly a phenomenon of the second half of the century, of the 19th century, the age of increasing precision. And then those questions came up. So we shouldn't blame Ampere too much. Perhaps Felici could have known.
Weber didn't say anything about the setup, only about the measurement.
Mainly about the measurement, yes.
Thank you.
Concerning the reception of Faraday concept about induction, you mentioned silence in public opposition. In your opinion, why silence in public?
That's an interesting story about Faraday. Of course, Faraday was a highly respected figure. He was member of the Royal Society. For a time, he was asked to be president, which he refused. He was a public figure, so people liked him for his experimental excellence, and there was no. I think there was even no criticism of these concepts because people didn't know what to do with this. These strange lines of force.
Too much geometry on rather than
yes.
algebraic.
Too strange, people would have said. Too strange to be discussed. Weber, in 1845, went even so far to say, we don't have a law of induction. Of course, Faraday would have protested, but a law of induction formulated in terms of lines of force doesn't count.
Okay, thanks again.